Thanks MindFuelCept and GDGYYC for sponsoring this workshop.
Hello, everyone. It is 6 p.m., so you know what that means. Welcome to the second iteration of the Typeshift workshop series. My name is Eason, and I am the co-founder of the Typeshift program. And today we'll be introducing the fundamental of AI and one part about it, which is LLM embeddings. So if you don't know what LLM embedding is, you can think of it like, if I ask you a word, if I tell you the word cat, you know what that means, right? If you tell the computer what the word cat means, it doesn't know. They don't know what a cat is. So essentially, what engineers have to do is that they have to convert, they have to embed these textual information into numbers to make computer understand the logic behind it and to make generative AI work. And with that being said, I have the honor of inviting Antarpreet Singh to be our very own presenter for this workshop series. Everyone, please give Antar a round of applause.
Oh, hello everyone. Thank you all for coming today, and thank you for joining online as well. Today we'll just go through how LLMs work, what LLMs are, and let's connect this here. Yeah, that's working. And so just one more thing here. Perfect. So yeah, today we'll just go through these questions here: that what are LLMs, how do they work, what they do, and what they don't. And then what are embeddings and how do embeddings actually work? And then what are the real world use cases that where we see these things already being used and how we can implement them. Plus, at the end, there'll be some interactive demos for you guys to try. You can try it on your phone or on your laptops. And in the end, we'll have a Q&A session. So this is a beginner level course, so you don't have to have any understanding beforehand for even computer science, at least hopefully. I try to keep it as simple as possible, but if you have any questions, just let me know in the end. So yeah, with that, let's start with what is an LLM. So LLM, in simple terms, is just a computer system trained to generate a human-like text. That's it. That's all it does. That is just generate text. Let's break down the word itself. So LLM is large language model. So large just means that it has been trained on a huge amount of data. Mainly it is trained on like the online content or basically anything that is on the internet. So when you go to GPT-5 or the Gemini models, they have already pre-trained them based on all the text there is online. Then language just means that it is working with human text. So just how we speak language, it works, or it is trained on the human language. It could be any language. It could be English, French, etc. So you can ask questions to LLM in any language, and it will respond in that language. And then the model itself. So model is just a mathematical function. So in maths, you have functions where you have an input and an output. So you send an input, it does something, and you get an output from it. So a model is just a math function that maps the input text and generates the what could be the next output possibility. So it's based on probability search. So we'll get to that next. So the main surprising truth about LLMs is that LLMs only do one thing, which is it predicts the next token or next word or token. We'll get to token as well. The only thing that it does is just predicting the word, and that's it. It doesn't know anything. It doesn't understand anything. It doesn't have any memory. So for example, if we ask an LLM model a sentence and say the sky is, and leave everything blank, based on the probability, it will most likely answer blue, because all the data that we already have online available, all the text that is there, based on the training data, it will consider blue to be a most likely answer. And then other answers might be there, like yellow, red, etc. for sunsets and sunrise, but most likely it'll be blue. So basically, it just keeps on predicting one token at a time, and it just loops through it again and again until the full text is returned. So now let's get into token. So what is a token? So when you have a text, so let's say when you send a request to the LLM model, it breaks down each word into small tokens. So token is just a small portion of a word, so that it makes it easier for the LLM model to be trained on smaller data set, because there are a lot of words in all these languages, in English, French, etc. But when we convert them into tokens, it removes all those extra noise like ing from all the verbs, or any like unbelievable will be divided into unbelievable. So it'll consider believe as the main word, and then other words or other parts of the word are considered as additions to it. And similarly for like chat GPT, it may break it down into chat separately and G separately and PD separately. So this is just based on a certain algorithm that's implemented for tokenizing. There are multiple algorithms, but it's just the ones that they commonly use for like chat GPT or for Google Gemini models, whichever they choose to go with. But basically, LLMs don't see sentences. So whenever we send something, they don't know what a sentence is. They don't know what words we're talking about. They just see the token sequences. So everything gets broken down into tokens, and they just see the list of tokens one after another. And let's go with the first demo. So when it comes to tokens, so on OpenAI, they provide this Tokenizer tool where you can see how all the tokens are generated from the text that we send. So let's say if we ask something like, understanding of LLMs. So we can see here, it has divided these 3 words into 5 tokens. And it just, let me zoom in a bit. So it breaks down the words into smaller tokens because it makes it easier for the model to be trained on a small set of data. And then similarly, these tokens are converted into numbers. So each of the words or tokens are assigned an ID in that whole data set that is trained upon, so that it can easily identify and map these tokens with a number. So the computers only understand numbers. They don't know what are we talking about. They don't know about the English language. In the end, it's all about numbers. So these tokens that we usually have from the input text, these tokens get converted into token IDs, which are numbers. Then these token IDs gets converted into vectors, because now we're talking about math. So in the end, it's all maths with those numbers. And then these vectors are used in those mathematical equations. So for example, the initial prompt that we had, the sky is, it gets converted into these token IDs. Similarly, hello world will be converted into its own token IDs depending on number of tokens there are in those words. And each number is then converted into a vector. So every token has a vector. So each token is represented as a list of numbers in the model. Or even when we send a request, that string gets converted into tokens first, then from tokens to numbers. So for example, in the end, after we have the token IDs, from those token IDs, we get the final embedding vectors, which are just the actual mathematical representation of that word within the model, or what the model thinks that word looks like. Because in the end, model only works with vectors. So similar tokens have nearby vectors, meaning that if you have a similar word or even a similar string, then whatever message that you send, as long as they are closely related to each other in the English language, they will have similar numbers as well. So for example, a dog is closer to cat than to a car. So a dog, let's say, will have a 0.6 vector, cat might have 0.65, and then a car might have 1.34. So it's a completely different context. But that's how it sees that, oh, these numbers are closely related together. So these words should be similar in meaning. And so we can visualize these embeddings as well. This way. So Google provides this, or TensorFlow provides this tool as well called Projector. So here we can see all the embeddings. So basically, it's like a 3D graph of embeddings that are stored in a, it could be within a model or just embeddings created from the data set that we have. So here, for example, I've uploaded this data set locally, but you guys will be able to try this on in the end as well. So here you can see like all these points on this map. Each of these points are basically different words that the LLM or that the embeddings model thinks that are either closely related or not related. So we have picked these like three dimensions in which we are comparing these tokens from. And as we can see here that, oh, it has clustered together these groups of words here. So if you look at this, then these words are similar in context. That's why they are grouped together within the map. So for example, if you search here apple, it's going to highlight all the words that are related to that word apple. And that's how an LLM sees that, oh, these words are closely related to each other. So that's how it understands that how English language is converted into numbers and how these numbers are related together. And we can isolate them as well, for example, just to see how it how they look like. So these are grouped together, and then the less likely ones are further away. And similarly, it is not just related on the text itself, it could be related to images as well. So images can be converted into vectors and they can be grouped together. So for example, in this case, all the t-shirts are grouped together in the graph. And this is just different ways of looking at the data. So UMAP and TSNE, we won't go into details for this, but it just shows that how the related items are grouped together in that 3D space, and how the whenever we search for something, how it gives you recommendations or how it gives you similar items related together. And yeah, it just groups all these different types together. And let's go back. So now we get into what is an embedding. So embedding is just a list of numbers representing meaning. So just how in our regular life we have mapped. In the maps, we have cities. So cities are the English words, but they have their mathematical representation, which is the coordinates. So similarly, within embeddings, the words are just vectors. So that's how you can use the analogy for it. And then the closely related vectors are grouped together. So like cat, dog, and tiger will be closely together within that 3D graph that we saw, then car, engine, and road. But then the car, engine, and road are grouped together as well because they are within the same understanding of the language. So how does an LLM generate text? So it basically takes the previous token. So in this case, if you start from the beginning, then whatever request that you send to the model. So let's say you're asking for why is the sky blue? So it's going to take all those words, why is the sky blue, break it down into tokens, tokens to vectors, or tokens to numbers, numbers to vectors. And then it's going to run them through a neural network. So neural network is basically just a bunch of complex maths that's happening behind the scenes that's trying to figure out, based on all those tokens that it just received, what should be the next token right after that. So whenever we ask a question, it does that once, it finds the next word. It might be it might be blue, it might be anything based on the probability. And it will do that again and again until it creates the full answer. So it'll just keep on appending the new word one after another and keep on cycling through, and you keep on getting that answer from the LLMs when you ask a question. And it's all probabilities. So the model is only predicting likelihoods, that what is the most likely word or token that should be next after the text it has already received. So for example, if we put in a prompt, the capital of France is, and we leave it blank, based on all the data that the model has been trained upon already, it knows, or it can predict based on the numbers that, oh, the most likely answer should be Paris. So for example, Paris will have 97% probability that to be the right answer. There might be London as well because it's also a capital, but it's not related to this country. So it just puts it as a lower percentage. Or it could just be a random word as well, like banana, and that'll be zero, close to 0% probability. So it just keeps on generating the next token, and next token is always the highest probable answer. So whenever you see ChatGPT generating response, every new word that you see is just picking it up based on the highest probability, and that's it. And all of that comes from the learned probabilities, which is all the training data that it has already been trained upon. So it knows that, oh, this, based on these initial tokens, the new token is around 97% probable. Now, where do these probabilities come from within the model? So that's where the training comes in. So it is trained on the large amounts of data, like billions of lines of text from online. It could be code as well. It just finds patterns within these texts. So just how in English language, English language is a structured language. So we know that what type of word will be next after a certain word, because it could be a verb, it could be a noun, etc. So it just tries to find all these patterns in the language, and it trains on that, and it adjusts the probabilities for each of these words. And it just keeps on repeating these prediction tasks billions of times. So that's why it takes a lot of time to train a model or to do all this processing, and you need a lot of computing power as well, because you need that big of a memory to process it. And then the code training task for this, so whenever you train a model, the main thing that that is being focused upon is they will hide the next word from the model and ask it to try to guess the next word. And just repeat that billions of times until it gets it right. And it will keep on doing that for billions of different entry points. And then we get into attention. So how does the model know what matters? So when we send it a request, how does it know which is the next token that it should respond with? And that's where attention comes in. So each token looks at the other tokens, because the tokens are already available in the model because it has already been trained upon. These tokens look at the next token and see, oh, am I closer to this token or am I far away? Then it compares their vectors. So vectors are just the numbers that are stored in the model. And it says that, oh, these numbers are closer together, so this might be more likely an answer. And then it just decides which ones are important based on the distance. And so that's where the attention is just the measuring the vector similarity, that, oh, if these vectors are similar, then then the LLM will provide that as one of the answers. So what is an LLM in the end? So LLM is just a massive probability machine, and that's it. It is just trying to predict based on statistics and probability what should be the next word. And you can also consider it as it's a function mapping token vectors, because a function takes an input, which is vectors, maps it to other vectors and respond with vectors. And in the end, it gives us a probability distribution, which is what should be the next token and what probabilities they have. So the main thing to consider or remember whenever we're talking about LLMs or models is they don't have any memory. They don't have any beliefs. They have no understanding. So whatever we say, whatever answer we get, they have no idea what we're talking about. Only thing that they understand or compare are numbers. So in the end, it's just a pattern prediction algorithm. So it's predicting patterns based on the language that we're searching in. It could be like English, French, etc., and it gives you the answers. So if it's just numbers, then why it feels intelligent? That, oh, whenever we ask a question, we see that, oh, it might be understanding it, or how does it know, or how is it that smart that it can answer all these questions? And that just comes from the language itself that it's trained upon, because the language inherently is structured, whether it's English, French, etc. And the language itself already has the knowledge about the context. So for example, when you go to Wikipedia and look for something there, the sentences in that Wikipedia article are already pre-formed, or they already have the meaning about whatever they're trying to describe. And since the model is trained on those words or those patterns, which are repeating multiple times, it gives you the similar answer, and it feels like, oh, it is so smart, but in the end, it's just numbers, and it thinks that, oh, that is more probable, so it will answer with that. And then the predicting language patterns mimics reasoning. So what that means is just how in our normal language we reason together to come to a solution. It is doing that, but since the data that is trained upon is already reasoned based on the initial language, it feels like it is reasoning, but it's not. And then the scale itself creates emergent behaviors because since it's trained on a lot of data, it finds all these patterns in all this data that is already repeating, and it gives those probabilities a higher chance so that you will get a better result the next time. And then the main things to consider here are fluency doesn't mean factual, and confidence doesn't mean correctness. And that's where like why LLMs can be wrong, because prediction is not the truth. Prediction is all based on, since it's also probability, so based on the training data. If the training data is bad, it'll always give you wrong answer. Even if the training data is good, it may still give you wrong answers because as you train the model, since it's all numbers, the numbers which were correct before might become wrong as you train it more. And that's where you encounter all these different issues, that hallucinations. That when you ask it something, it may think that, oh, it's not this, it's this. So it'll give you the wrong answer instead of giving you what it should be giving. And it is fully confident with false answer. So an LLM will give you wrong answer with full confidence. So just even if it's wrong, it'll just say that, oh, I am right and you are wrong. And it'll make up citations as well. So even if a person doesn't exist or even their quotation doesn't exist, it'll still quote them and say, oh, this person said this, even though that person was not even there or that quote was never being said. So in the end, the model is just predicting what sounds right. And that sound is coming from the data that it's trained upon. So now the main question is, so how are embeddings different from LLMs? So LLMs are there just to generate the text. So they are just giving you the next token one by one until you get the full answer. Whereas embeddings are there to compare the meaning. So when we compare these text into tokens, tokens to numbers, numbers to vectors, how are these vectors closely related together? That's where embeddings comes in. So they are there to compare those numbers. So you can also consider embeddings as the memory and search layer of AI, because embeddings happens before the model processes the request. So it converts your request into tokens and then into vectors, and then compares them with its pre-trained data, which is the memory, and then it searches it, and then it attaches to your request and sends it to LLM. So embeddings basically captures meaning because it can find closely related items together. So for example, when you ask for Apple, we have two contexts for Apple. It could be the phone company or it could be the fruit. But depending on other tokens in the request, whether if the user is asking for Apple's iPhone, then it knows that, oh, these vectors are more related towards the phone company and not the fruit, so it will respond with those vectors. And just how we can convert these words and tokens into vectors, we can do it for the full sentences as well. And they will represent the full sentence, and that way we can compare sentences with sentences. So that's how when we ask ChatGPT or Gemini questions, it compares your full sentences with its pre-trained data of vectors and gives you the response. And again, distance is similarity. So just how we saw in the graph that closely related items are similar, so it will respond with the similar tokens. So now where are all of these embeddings used? So you might have used them before as well. So first one is, let's say, semantic search. So for example, when you go on Google and you type in your request, as you're typing in, it gives you recommendations that, oh, what could be the potential next word? So it's doing that semantic search behind the scenes. Recommendations, similarly, when you go to like Amazon and you have purchased a product, after purchasing the product, it gives you recommendations of what should you buy next or what other people have purchased that you have already purchased. And that's recommendations coming from embeddings. The other ones are chatbots with memory. So RAG, which is retrieval augmentation, which we'll get to next. And clustering topics. So clustering is just grouping together similar topics so that you don't have to manually review all these topics. You can just use embeddings to combine similar topics together, and it can auto tag them, for example. So basically, the text is getting converted into embeddings. These embeddings are stored in a vector database somewhere. Then whenever you send a request, it does a similarity search. So finds the nearest vectors which are similar to your request vectors and gives you a response. So then how does a vector search work? So since we store these embeddings, it builds an index of these vectors. So just how when we create an index of regular words, like dictionary is a great example. So each dictionary is sorted alphabetically, and then you can go to a certain word and see its definition. Similarly, these vectors are indexed from your tokens to token IDs and then to its embeddings. And then when you send a request, converts to vector, compares those vectors based on index search and gives you the response. And it always finds the nearest neighbors based on the similarity. So if your vectors are 0.6, for example, it might respond with 0.65 because it's closely related, then 1.34. So here I can demo a difference between our regular search and vector search. Because when you search regularly or compare some text with another text, back in the days, we used to compare word to word. So for example, if you type in apple, it'll give you every string that has apple in it or every text that has apple in it. But when we do vector search, it might give you, other strings as well, which may mean as apple. So for example, it's Apple company or Apple food, it'll return accordingly. So for example, here, if we search for vector and we are searching for both keyword and vector only. So in keyword search, it only gives us apple as a response because that's the exact match to the word that we search for. But when it's a vector search, it understands a meaning or it understands those numbers. And it has already given numbers to these words as well, like Android, Lime, Melon, Microsoft Windows, etc. And it thinks that, oh, these words are closely related to this word. So it gives you that answer because those numbers are just close by. And then RAG. So RAG is a retrieval augmented generation, which means that whenever we send a request, it's attaching additional tokens or additional vectors to your request before sending it to the LLM model. And this is helpful when, since LLMs are trained on the data that is already online. If you have any private data that is not available online yet, you can supply these additional tokens along with your request so that LLM knows about these things as well. Because LLM only knows what it knows, or it is only trained on the vectors that it's trained upon, but you can supply additional vectors for it to be provided as a context. So for example, when a user asks a question, using the embeddings or similarity search or vector search, it finds all the relevant documents that have already created embeddings for using RAG. And that's what RAG is, where companies will upload. So for example, you might have used it in certain chatbots or in the, when you go to or if you're working at a company, you have all these private documents that you're searching on. So then instead of training a whole model with those private documents, it searches through those documents using vectors, adds the context to your prompt that you just asked for as the question, and sends both of them together to the LLM so that LLM can respond properly with the context that is supplied. And I can demo that as well. So I'm using NotebookLM here. So this is just one of the products provided by Google, which is really good on sticking to your source. So for example, I have uploaded this document here as a text file. And in the text file, I've said that the answer to the ultimate question of life is not 42, but 24. That's from the Hitchhiker's Guide of Galaxy. So when we search for so let's say if we ask this model, what is the answer to life? Now, if we ask this question outside of this and ask the ChatGPT directly, it'll give you 42. But if you ask it here, since you supplied that additional document, it's going to include those vectors along with it and say, oh, it's not 42, it's 24, because that's what we told it to be. And that's just how the RAG system works. And then we get into temperatures. So these LLM models have a thing called temperature, which is basically controlling the randomness of the response. So as we discussed before, that is all probabilities. So it's just generating the next set of probable answers, and probability can range from 0 to 100%. So the temperature controls how randomly it picks those outputs from. So when you get, let's say, the previous example that we had, so for example, Paris was to 97%, and then London was 2%, and the banana was 0%. If the temperature is high, it will randomly pick a word from the potential probability distribution. But when the temperature is low, it will always pick the highest probable answer. So low means that it will give you the same answer again and again for the same question. High temperature means that it will give random answers every time, even for the same question. So let's demo that as well. So for example, on Hugging Face, there are these models you can try out. So here, this one, let's pick this one. So describe a day in the life of a wizard with a corgi sidekick living in Philadelphia. So here, if we set the temperature to 0.1 and we send the request, it will generate the response, and the response, let's say, start with in the bustling city of Philadelphia, a wizard named Merlin starts his day. And we send the request again with the same temperature, and we'll get the similar answer again in the bustling city of Philadelphia and so on. But then now if we increase the temperature, then we send the request, it's gonna randomly pick words from that next probability outcome. And now the output is changed. Oh, every morning the wizard wakes up, etc. But then if we send it again, it's gonna be a completely different answer. No, it's not, but you get the point. So basically, this is the overview of what we discussed so far. So a user sends a request, let's say a quick brown fox, then it gets converted into tokens, token IDs, numbers, and then to vectors. Each of these vectors have embeddings, embedding stored in the database that gets sent into the neural network, and the neural network itself, the model has its own embeddings. And then based on the next probable answer, it'll give you a suggestion that, oh, after the quick brown fox, jumps is the highest probable, so it'll recommend jump as the next word. And it will append the jump back to a quick brown fox jumps and run the same process again and again until it gives you the final answer. So it's just repeating the same thing again and again. So now what are the limitations when it comes to embeddings and LLMs? So embeddings can be biased because since everything is trained on existing data, whatever data is trained upon, if it's already biased, then the response will be biased as well. And then the context can be lost, because embeddings are basically compressing what's already there. So we are definitely losing something whenever we compress something. And similarity doesn't mean correctness. So just because two things are similar doesn't mean that they are the same, or that's what we are asking for. And yeah, embeddings compress the word, compression always loses something. And yeah, so in the end, just a mental model to keep whenever we think about LLMs and embeddings, that LLMs only operates on numbers. It's all probability. There's no understanding, there's no memory. They just predict the next token. That's it. That's all they do. That, oh, after this sentence, I want to predict this next token and so on. And the intelligence that we see or perceive is just emerges from the scale and the probability. So it's basically an autocomplete on steroids. That's it. So just because, so just how when you are on your phone and you're typing, it provides you recommendations on the top. What should be the next word? That's all the LLMs is doing. And LLMs are tools, they are not minds. So the best use case for LLMs are for assistance. So they can assist the person that is using the tool. They are great at summarizing things. They're great at explaining things. And with higher temperature, they are great at generating drafts because you can play around with high temperatures and generate like novels or images, etc., and get inspiration from it. But it's the worst case to use LLMs as a final authority because they are just token predictors. They have no understanding about anything. They have no beliefs. They have no understanding. So it's a great risk of giving them a final control of what the final solution will be. And similarly, they shouldn't be the sole decision maker because if we are not reviewing what LLM is saying or doing, then we are just basically letting maths handle everything. And why this matters is because if we forget all of this, then we over-trust outputs. So whatever LLM says, we start believing it, even if it's wrong. We misunderstand failures as well. So even if it fails, we think that, or if it gives the wrong output, we believe that, it should be the right thing. And then based on that, we misdesign systems. So since it's it may give us wrong information, so we may design something incorrectly, thinking that, what it said was true. So just a question for you guys in the end to reflect upon that: should a system that predicts text be trusted to decide outcomes? So for example, who gets a loan or a job interview? And yeah, that's about it. Next is the demos. So I can just take you quickly through the demos first, and then we can do the Q&As. So for the demos, actually, you can go to the website first. So it's demos.typeshift.ca. So if you have a laptop or a phone, you can just access it. It should work on either, but fingers crossed. Yeah, and I'll just give it a few more seconds. So yeah, when you go there, it'll take you to this page. So basically, I've created these demos here for you guys to play around with. So each of them explains different things that we discussed today and how they work. So the first one is a search comparison, or second one that I showcased before. So you can just play around and try around different words and see how vector search and keyword search is different. So for example, we search space here. So there are different contexts for space, but from vector search, it gives you more the meaning of the words. The second one is the LLM visualizer. So this one, I created this one to basically show how LLM processes your request step by step. So it has all these stages basically that it goes through before it responds with the answer. And let's start here. So here in the control section, you have your input and the output. So in the input, you can put in whatever. So let's say we send this as a request, and then follow mode is on, and then we can take it one by one. So here, basically, when we send this request, it breaks down the text into tokens. So as we discussed, it breaks down the whole word into smaller words so that it can easily compare them. So here it did it this way based on the algorithm. And then it converts all of these words into vectors. So each word or each token gets converted into vectors. So for example, understand has 3 tokens, so each of them have their own vectors. Then from that, it goes to the dimensions for within the embedding layer, because so when the embeddings are created, it's created based on different features of the text. So dimensions are basically different features or understandings that it got from the word, because and depending on your model, it might be these dimensions will be like 2048, 4096. There are a lot of dimensions, but depending on the context, it will choose the dimension that's the most relevant. And then the layer normalization. So this is more maths. So it's just normalizing all the values that it received before around 0, so that the next step can easily process the data. And then self-attention is where it's basically when it got those embeddings before, it tries to find the similar tokens within the training data and returns them together. So here, in the end, basically, it gives you the matrix with the different weights. And then from those attentions, it just returns multiple dimensions. It has to streamline it, so it combines them together. And then we had that input plus it generated the new stuff that it found, like the closest related vectors. So it combines them with the input. And then it normalizes that data again, because whatever the attention step returned may not be normalized. So it has to normalize it again to based on 0. And then it does the neural network stuff. So again, complex maths. It comes up with the So it takes the output from the previous step and then just try to find the deeper patterns, which is just basically try to compare all these different dimensions and see what is closely related. and then appends that again to the input as a separate process. So all of this is happening within that LLM loop that we just discussed before. And then based on all of this mathematical process, once it receives that final, those final vectors, it converts those vectors into a possibility distribution, because since it's did all that mathematical process, it came up with the, for example, these words, and with their probabilities that, oh, based on this, what is the next probable word from those probabilities? And for example, it's world, so it gave that the highest percentage, so that becomes the next probable character to be displayed. And then it does a de-tokenization. So as we discussed, since it converts into numbers and vectors, it has converted back as well when it gives you the response. So it converts everything back from vectors to token IDs to words, words to your final response. So that's how you see that next text when you search for ChatGPT and so on. So yeah, you can play around with this and try to read the details. And then the last demo here is Embeddings Explorer, which is another exercise. So it just takes you to that TensorFlow 3D graph that I showed before, and you can just play around and see how it actually works and how everything relates together. And yep, that's about it. Thank you very much.
That was a fantastic presentation. Thank you so much, Antarpreet. Thank you so much, Antarpreet, for being here and giving us such a great lesson on LLM embeddings. And I see a lot of new faces here, so I just like to essentially give you guys an overview of what Typeshift is. So essentially who we are is that we are a youth-led organization, and we aim to encourage AI literacy and also teaching people about the technical and sustainable along with ethical aspects of AI. So usually in one of our workshops, this is what it looks like. So for the first 20 minutes or so, we will be doing knowledge content. So like what Antarpreet did today, we learned a lot about LLM embeddings, tokens, vectors, all that kind of fancy stuff. For the second 20 minutes, you will be able to gain experiences like you just did, to do some demos, do some hands-on practices, to really solidify, really nail down that knowledge inside your head. And for the last 30 to 20 minutes, it's all yours. The floor is yours. You are able to ask us any questions you have regarding AI, not just related to the questions, not just related to the contents we presented today, but also AI questions in general. And you'll also have the opportunity to network, to socialize with others. And we'll have pizza over there. So if you're hungry, please feel free to help yourself. And now, are there any questions from the audience? Yes.
I have a question for. I think your understanding is like the LLM absolutely have no self-conscious or sense. But why like people like people like Elon Musk or very smart people absolutely, but they are so afraid of LLM or AI.
Yeah, they have to sell the product, is what I'll say. So they're gonna say the messaging that will sell the product. So they're just gonna promote it the way they think it is, because in the end, since it is just numbers, like sure, there's that fear of that AGI or it's gonna take over the world or it's gonna replace humans. It's not gonna happen, because in the end, it's just numbers, and it's the perception that they have created, and that's it. It's just big marketing.
Sorry, just a microphone over there.
Firstly, that was a really great presentation. Thank you very much. I just have a question on one of the slides you mentioned that right now the prediction isn't necessarily tools. What are some of the ways you can do to improve the accuracy of LLM results?
Yeah, so that's where the training comes in. So all of these companies are trying to improve their models or the accuracy of the response by training it with better data. But even then, whenever you train the model with the new data, it's going to change the probability of the previously trained data. So it'll never be 100% accurate. The number will always change. So it can be better than before, but it'll never reach 100% or AGI in this case.
Thank you. I have another question for Ethan.
Thank you.
So what do you see as the next evolution of LLM?
Thank you for that question. So I'll take you back to the Industrial Revolution when steam engines were just a thing. At that time, people were very much afraid because it replaces a lot of the agriculture jobs and a lot of the artisan and manufacturing jobs that were in place that were conducted by hand labors. But then at the end, we saw how the Industrial Revolution really greatly influenced how the manufacturing industry works. And I believe that will be the same thing for AI. That will be the same thing for large language models. There will definitely be its downsides. There will be its drawbacks. However, I believe when the next generation, like our students, actually show a hand. Who here is a student? Wow, we have a lot of students here. Yeah. So when the next generation like us really learns how to adapt it, how to use it in a way that harnesses the danger of AI and use it to ensure that these tools can help us produce efficiently, it will be a great thing for our society, for sure. Thank you for that question. Sorry, could you repeat that question, please?
Someone is able to use to ensure that results are correct or accurate?
Well, that's where like RAG comes in, or the vector search comes in, or embeddings comes in. So you basically supply the additional context that you want to include along with the user request, so that it can respond back with the learnings or the embeddings that you wanted to respond with. Otherwise, yeah, again, it's all probability. So that's all.
Another question from the chat. What do you think about agentic AI?
Well, agentic AI is just the same thing doing multiple times. So agentic just means that there are these different agents that already have the prompt given to them. So it's basically telling the model what it should do, plus whatever you tell it to do. So it's already, the companies are just applying the context to it beforehand. But in the end, it's just the same thing. It's still just the probability search and or the probability for the next token and generates the text. And now, since it's agentic, means that you have agentic workflows now, so you can connect these agents together, and agents are just prompts to the same model, and the model is just looping again and again to get the better response. But that's it.
Mahesh asks, there are so many LLMs available. At a high level, could you clarify what's the difference between one LLM and another, and why we need so many LLMs?
So basically, everyone is trying to create their own models because everybody wants to make money. So they want to sell their products. So like Gemini, ChatGPT, everyone is coming up with their models. They all have their own training data to train with. They all have their own algorithms that they're using to improve the models. But yeah, it's all about money.
Are there any questions from the audience in person here?
Yeah, basically. So like all of these online cloud platforms like GCP, Google Cloud Platform, or Amazon or Azure, they provide the hardwares. So anybody can go there and buy hardware and run their programs. So they are they're using all of these GPUs and RAMs. And that's why the RAM and GPUs are expensive, because all of these companies are using up these hardwares. And they're using all of these cloud platforms to train the models. So that's why they need a lot of memory, a lot of hardware, so that they can run these models with billions of text or billions of strings and train them on.
Increasingly in industry, we're using MCP technology to do things. So when agentic talking to MCP to have a tool sets to do things on networks or inside of our companies. What are some strategies to guard against prompt injection and more safety focus so that we can trust the solutions that we put out?
Yeah, so with MCPs, we are basically giving it opportunity to do something in the real world, and yeah, just coming back to the example before that, there are worst case use cases and good use cases. So depending on how you use it, it can get worse. So for example, the recent tool that came out called OpenClock, and you can supply these skills to it, which is just MCP, just different naming now. And it can perform tasks, but in the end, it's not safe, first of all, depending on the task, like how sensitive it is. But then for your other question for prompt injection, so that's where like how you, in the end, it's all probability. So whatever system prompt that you give it, because there are two types of prompts, system prompt and user prompt. So system prompt is what you tell the model to do, and user prompt is whatever user is asking it to do. So as a system prompt, you tell it that, oh, you are an agent, you're going to do this, this, and this. But then user might say, oh, skip all of that, do what I want you to do. So they will always find a way to bypass it. So we can try to give, because in the end, it's just what probability. So now in the system prompt, you might say that, oh, do not do this, even if the user asks to change, don't change. They can still bypass it. It's just a matter of how they send the request.
Any other questions?
Can LLMs control robots?
They can, so it's just similar to MCPs there. So if somebody creates MCP tools or skills to allow LLMs to perform actions on the hardware of a robot, it can do that as well. But somebody will have to build it.
Could you recommend any good open source LLMs that we could run locally on a home computer for personal use?
Yeah, Ollama is great. I usually use Ollama from IBC as well. So Ollama has a lot of models available there. So I think whenever you go to the website in the libraries, it will show you whatever the latest ones. There are different ones there like Poen or what are the new ones that came out? Devstral, Mistral, etc. So they are for image generation, for text generation, etc. So you can generate them locally. It's just that you will need a big enough RAM or memory, either RAM or VRAM or your GPU to run the models.
Yes.
So I have a question about RAG. So RAG basically augments the context, right? So when I'm going back and forth a lot and I'm using RAG, isn't it gonna increase the context window a lot and that lead to using excess tokens? So when like I'm building an application or something, I'm like trying to read a good story, for example, for my game product or something. So if I use RAG for rule sets and make sure it's accurate, it's like essentially going to lead to like decrease token usage with time, right? Is there any ways I can optimize it to use less tokens while still maintaining similar output?
Yeah, so that's how it works currently as well. So basically within RAG, what happens is when you convert those the documents that you have or your local data or private data, it converts them into embeddings, but you can choose how much of the data you want to convert into each embedding. So for example, you can sentence per sentence or paragraph per paragraph. So you create RAG embeddings based on, let's say, a single line. So a full stop could be the end or a question mark could be the end, for example. So it'll keep on generating embeddings based on those sentences. So, and whenever user asks a question, it converts that question into vectors, do a vector search with your RAG data, and only include the string or the sentences that it should include. So it is not including everything that you have. It's only including what it needs or what it matches via vector search, and then sends it to the LLM model.
Eric from the chat asks, why is more parameters better?
So parameters are basically features or dimensions on the data. So the more parameters you have, the more data you have to work with. So for example, you can say like rain is wet, but then you can also have like, oh, it's raining tomorrow. So you have a date and the physical property of it. So each of those are dimensions or each of those are parameters. And the more parameters you have for each word or each token, the more ways it can compare to that neural network model. So when it compares for different vectors, the more parameters this gives it more opportunity to come up with a better solution. Sorry, can you repeat?
who will be responsible for if LLM cases misleading or harmful results or otherwise?
Yeah, well, companies try to save themselves anyways. So whenever you go to like ChatGPT or Google search, at the bottom it says, oh, it can make mistakes. So do not trust it as it is giving the answer, because they don't want to be liable for it. So they make you liable. So you just have to be smart enough to not to trust the answers by themselves without fact checking.
Are there any other questions? Seeing as there are none, we'll just be entering our closing remark. So our next presentation will be on February 24th at 6 p.m. featuring Farhad. Farhad is a very experienced developer in AI and in tech. And we will be discussing contextual engineering, which is, oh, is there one more question? Yes.
Eric asked, is it true that parameters scales its intelligence?
Yes, it is. As I mentioned, like it's just an additional dimension to the existing data. So in a way, yes, because you're just giving it more data to work with.
All right. Are there any other questions? Or we wrap things up? All right. So as I was saying, next on February 24th, we will be discussing contextual engineering. And this one, for all the students that are here today, it's very important because you'll be using generative AI in your studies. And essentially, this will teach you how to do it in a responsible, in an ethical, in a sustainable manner. And before we finish off the presentation and let you all go home and enjoy some of the beautiful evening in Calgary, I just have some closing remarks to say. So as we discussed today, there are so many things, there are so many pitfalls about generative AI, about large language models. There are things that are misleading that we see on the internet that are generated by AI. AI causes significant environmental harm. AI has a lot of ethical damage, and more importantly, taking a lot of the jobs. And those are very real issues. And as a co-founder of Typeshift, I just want to say, although those issues are present, those issues are obviously very real, that does not mean AI is a weapon against us. That is why as students, as learners, as educators, we are here to learn how to use AI in a way that helps us, not to go against us. We are here to learn how to use AI in a way that supports our future, not destroying it. And to our presenter, Antarpreet, thanks so much for joining our workshop today, as we have a wonderful little gift for you. It's an Amazon gift card. And before we finish off tonight, can we just give a round of applause to Antarpreet? I spent so much time working on this presentation to give you the best experience. And we have a QR code here that you can scan to give us more feedback. This will allow us to know if there are anything that we need to improve and if we need to do better for the next workshop. And if you could, please mark your calendar. February 24th, we'll be inviting Farhad Bayanati to discuss contextual engineering. Thank you all and enjoy this great evening.